Solids and liquids are easy to handle, right? It's a simple job to measure them in the lab. But what do we do with gases? For this, we're going to need a clever trap. I'm Matt Queen, and this is Collecting Gas Over Water. Gases are all around us, but they're clever. To measure them in the lab requires a clever trap. This is a gas trap. Let's use it to determine an experimental value for the ideal gas constant R and see how well it compares to the known value. This is solid potassium permanganate. When it's heated, it decomposes to make oxygen gas. When we heat up the potassium permanganate, the O2 gas will travel through the tubing and exit into the bottom of this inverted measuring cylinder filled with water. It will then bubble up through the water and displace it from the top down. As we do the experiment, we'll see more and more gas gathering in the top of the cylinder. We can experimentally determine the pressure, volume, temperature, and moles of O2 collected. These can be substituted into the ideal gas law to determine the experimental value of R. All right, let's heat things up. All right, so you can see that we have this amazingly molten potassium permanganate releasing its oxygen up and over through the tube into our inverted graduated cylinder and displacing the water from the top down. We're trapping the oxygen gas. All right, I'm just gonna take this cap and place it over here to prevent backflow, and we'll let things cool off. Now that things have cooled off, I'll remove the test tube and weigh it. We weighed the test tube before and after the experiment. We lost 1.195 grams. The decrease in mass is due to the oxygen that we lost from heating the test tube, and we collected it in the cylinder. The moles of oxygen is therefore 0.0373. The temperature of the gas is the same as the temperature of the water above which it's collected. We determined this by reading a thermometer. It was 25 degrees Celsius, that's 298 Kelvin. We can measure the volume of the gas using the gradations on the cylinder. Looks like it's about 975 milliliters or 0.975 liters. If the line of the water in the cylinder is even with the line of the water in the pool, the pressure in the cylinder will be the same as the pressure in the room, which we've measured using a barometer. We read this to be 0.993 atmospheres. But wait, anytime we do an experiment, we should always think, is there something else that I should account for? According to my research, we can assume that the volume of the molecules in the ideal gas is 0. But it turns out there will also be water molecules in the gas phase above the surface of the liquid. These water molecules exert a vapor pressure that depends on the temperature. If we picture the gas above the water in the cylinder, there are some water molecules as well as the oxygen molecules bouncing around. So, how can we focus on just the oxygen? Well, we know the vapor pressure of water at all temperatures. At 25 degrees C, it's 0.031 atmospheres. The pressure due to the oxygen is therefore just 0.962 atmospheres. We can substitute these values into the ideal gas law to determine R. As always, we need to be extremely careful with our units. This gives us an experimental value of 0.0843 liter atmospheres per mole. The known value of R is actually 0.08206 liters atmospheres per mole K. We were only 1% off. That's a level of accuracy that takes some real care to produce. So there you have it.